So since I forgot to turn on recording and I just turned it on now, I'm just going to go back over this a little bit for people that were not here to hear what I said previously. Okay, as I said, the mean is a population parameter. We rarely know what that is unless we measure everybody in the population. The standard deviation, sigma, of the population is also typically not known, okay, unless we measure everybody in the population and calculate standard deviation. But a lot of situations we run into, we say to ourselves, we've done other studies which are very large, a lot of people, or maybe even whole populations, where we kind of expect that based on those other studies, maybe we do know what the population standard deviation is, even if we don't have a good estimate of the population mean. So in a case like this, we might say, well, gee, I take a sample of size 36. Well, that sample of size 36, I calculate what the mean of those 36 people are. Well, the mean, which I indicate as mu for the population, and if I take a sample of size 36 and I find the mean of those 36 randomly selected people from that population, well, then I call that x bar instead of mu. So x bar is an approximation of mu. We don't know how good an approximation of mu it is, but it's best we have because we only have a sample of 36 people to work with. Right? Now, similarly, if we had a very large sample, or if we somehow measured the entire population and only found the standard deviation, well, then we could use sigma. However, most of the time, very often, we're limited to using to estimating what sigma is by calculating the standard deviation of those 36 people that we sampled. So just like x bar is an estimate of the mean, population mean, the standard deviation of those 36 people is a estimate of the population standard deviation, sigma. Well, that's all well and good, but now we want to put that to work to find the confidence interval. How well do we know what the mean really is? Okay, so if we use this cheat up here, where we say we know the population standard deviation, might be worthwhile doing because perhaps we do have a good idea of what it is. If we assume that we do know what it is, well, then we only have one area of uncertainty here, right? The estimate of x bar, how good that is at estimating mu. And we're saying that we know what sigma is already. So in that case, we use a z-table because we have a good idea what the spread is. We can say that x bar, if we take x bar and we look we look 1.96 standard deviations below x bar and 1.96 standard deviations above x bar, we have a 95% chance of knowing that the true population mean is between those two limits. Okay, so we justify using the z-table based on knowing sigma or having a really good idea of what sigma is. Problem is that if we don't know what sigma is and we're forced to estimate what sigma is based on the standard deviation, well, now we have two areas of uncertainty. We don't know how certain we are about x bar. We don't know how certain we are about the standard deviation. So in order to compensate for that, instead of using the z-table and z-score, we use a t-table to determine how far that spread has to be. Well, automatically because if we want the same level of certainty that we captured the mean, and we don't know what the population standard deviation is, well, then we know automatically that we need something wider than 1.9 standard deviations to the left and the right of the mean to make up for that uncertainty, give us a wider range. So we maintain that 95% certainty that we've captured the mean. So the problem with the t-table is there's not just one t-table, right? There's many t-tables. There's a t-table like the z-table for every sample size. Well, that would be untenable to really work with very well. So what we do instead is we just create a t-table that gives us the specific values of t that we need for what we're usually looking for. For instance, for the 95% confidence interval, for the 90% confidence interval, for the 99% confidence interval. And each one of these is going to have a different value of t and a different value of t based on the sample size. So you'll see that when we get to the table. You'll see that uh, for each value of sample size, for each sample size, you're going to have a different value, which is going to represent plus or minus whatever that value is. Let's say, for instance, for sample size 36, I'm going to take a wild guess and say it's 2.10 or something like that. Right? That's just a wild guess. That's not the real value. We'll look that up later, right? But you see that's wider. So that makes our confidence interval wider. It makes up for our uncertainty about what the standard deviation really is. And if that sample size were smaller, if that sample size were 25, it might be plus or minus 2.16, let's say, right? Again, not the real value, just an example. Now that makes it even wider to make up for our less certainty about the standard deviation sigma, right? And that makes us a wider confidence interval. And if we had a big sample size like 100, right? Well, that might be plus or minus 1.98, right? Instead of 2.10 and so on and so forth. Well, but a sample size of 100, gee, look how close that is to 1.96. In practice, many textbooks, many instructors will tell you if you have a large sample size. This is coming up from my first question that I got in the discussions group. Okay, if you have a large sample size, it's so close, why bother? Let's just use 1.96. Let's just use the z-table. There are some advantages to the z-table as well because it gives you real probabilities and stuff like that. It's got all those proportions in it and areas and so on. So why not just use that so we don't have to bother going to the t-table? So now the question is, what's a large sample? There's no real, there's really, like for instance, the speed limit on the Long Island Expressway is 55 miles per hour, right? However, you drive, when you're on Long Island Expressway, if it's not crowded, people are almost all going faster than 55 miles per hour, right? So what's too fast, right? There's no single answer to that, right? I mean, depending on the conditions, it's raining out, it's snowing out, and so on and so forth. Maybe 60 miles per hour is too fast. Maybe 80 miles per hour is too fast. It might depend on your driving skills, and so on and so forth. Who knows, right? So it's kind of the speed limit's 55. In other words, are 1.96, right, for a z-score. But really, in reality, sometimes we cheat a little bit. We go a little bit faster. What's too fast? A lot of answers to that question. Same thing here. What the real answer to what's a large sample is what's our tolerance for error. So if we're just doing a homework assignment and we're just learning, in other words, it's not a homework assignment. Let's say it's a practice example that we're doing, and we want to know if we're getting the answer right, and so on and so forth. And we're not too concerned about getting the exact answer. We just want to know if we're close, and so on and so forth. So we can move on to the next one, and we don't want to reference a table. You might say that 30 is a large enough sample size. If you're more concerned if it's actually an assignment you're getting graded on, you might not use a 1.9. You might not say it's a large enough sample size to just use the z-table unless you had a sample size, say, of 100, right? So I think most people are going to be somewhere between 30 and 100 in terms of what they would call a large enough sample size. I think last time Professor Weicker referenced this is he was calling 30. I think the textbook might use 100 or something like that. I'm not sure. You guys probably are more. You probably have read this stuff more recently than I have. For instance, what the textbook references. So you might have a better memory of it than I do. Okay, so it's really kind of a judgment call. So okay, let's give this a try now. So let's actually do a calculation that involves these situations for confidence interval. Let me close this out. Get a fresh page. Okay. Okay, so I'm going to give you an example. This is going to be, let's think about what these possible differences could be. We might want to find a confidence interval for mean. We might want to find a confidence interval for a proportion. Right? And in some cases where we're looking for confidence interval of a mean, we might know sigma or a large sample. Or we might not, it might be a small sample, and we don't know sigma, right? Well, confidence interval proportion is a little bit different. We have a special rule there. That special rule is that we have to have a sample size that's big enough to justify using the confidence interval proportion. So usually we're dealing with very large sample sizes of 100 or greater than 100, right? So usually we have a large enough sample that we can just stick with the z-score where the confidence interval of proportion is concerned. One extra rule: if let's say we got a sample size of 100, but the proportion, let's see, that 100 is, let's say we have a sample size of 100 people, and we want to know what the proportion of it, that proportion of that population is that is farsighted. Okay, maybe we found that 10 out of 100 people were farsighted. So 10 out of 100 is going to be a proportion of 0.10. Well, problem here is that we got 10 people that are farsighted and 90 people who are not. Most textbooks will say you want, even though you got a sample of 100, which is pretty good, you want both sides of this to be at least 15. Right? And you notice that if both sides are greater than 15, you're automatically greater than 30, kind of the other range that we talked about, right? So in this case, there's only 10 people out of 100, right? So one side's only 10. So that's a little bit tricky, right? So we might want to be a little bit careful with that. Most of the time, you're not going to see examples that'll put you into that trap. Usually, we're talking about large samples when we're talking about the confidence interval proportions. Okay, so let's do a calculation. Okay, so let's say I told you that we have a population and we're interested in finding the 95% confidence interval for the mean blood pressure for this population. Okay, we know that that we take a sample of size 30 of size I'm going to say 25, and we calculate the mean for that sample. The mean for that sample is 98. And we know from previous studies of much larger samples that the standard deviation is estimated to be 10. Okay, so we want to calculate our 95% confidence interval. So based on other studies or information that we've been giving, we think we know the population standard deviation well enough to say that sigma is equal to 10. I'm going to do this same example, except this time next time we're not going to assume that. Okay, so how do we calculate the confidence interval? The confidence interval is equal to x bar, right? The mean that we calculated based on the sample, plus or minus the z-score, because in this case, the z-score for a 95% confidence interval, or alpha over 2 is equal to 0.025. In other words, 2.5% on either tail, right? Or alpha is just equal to 0.05. You could look at it either way, but 95% confidence interval. I don't want to confuse you too much with the notation. Okay, so plus or minus the z-score that we need for a 95% confidence interval times the standard error. Okay, so x bar in this case is 98, plus or minus the z-score, since it's a 95% confidence interval and sigma is equal to 10, we know the z-score that we're going to use is 1.96. Of course, if we have 99% confidence interval, it would have been 2.58. If it's a 90% confidence interval, it would have been 1.64. Okay, now I'm pretty sure you guys by this point remember how we've gotten to these three numbers that we use over and over again for these various confidence intervals. It came from the Z table. So, for instance, 95% confidence interval is how far out you have to be in standard deviations. When we use the empirical rule, we just rounded it off to 2 standard deviations to the left and the right. When we looked at the actual Z table, it's really 1.9 standard deviations. That'll give you 2.5% tail in the area in the bottom tail and 2.5% tail in the upper tail, leaving 95% of the possible outcomes in between. Okay, so 1.96 times the standard error. We know we calculate the standard error is equal to sigma over the square root of the sample size. So in this case, it's 10 over the square root of 25, which is 5, is equal to 2. So it's going to be 1.96 times 2. Okay, so what is that going to be? That is going to be 98 plus or minus, and this would be, this is going to be 3 point, let's see, 12, 3.92, 3.9, is that right? Yeah, I think that's right. Plus or minus 3.92, okay, added to 98. So now we have a special name for this quantity that we're adding and subtracting. We call that the margin of error. Right, so you may see that term come up. Right, makes sense, right? 98 plus or minus this number, margin of error. Right, kind of seems obvious. Right, so if I add and subtract this, so if I subtract it, it's going to be, let's see, 94.08 and 101.92. I apologize if my quick math in my head is wrong, but it's, I think, pretty sure that that's what we're going to wind up. That's our 95% confidence interval. Okay, again, this, had we wanted a 99% confidence interval, this would have been 2.58, which would have made this 2.58 times that is going to be more than 5 added and subtracted, which would make for a wider confidence interval, which makes sense. If you want to be more certain, 99% certain you captured the real population mu, you want a wider interval to make sure you don't miss it, right? 90% would have been narrower, 1.64. Okay, so now let's assume that we don't know what sigma is, that the standard deviation is equal to 10. And we got that from these 25 people because we didn't know what the population sigma was. So instead of 10 being standard sigma, it's equal to standard deviation for our sample of 25 people. It approximates the population standard deviation, just like the X bar approximates the population mean. So what changes here? Well, again, X bar plus or minus. Now this time, because it's a small sample, we have to make up, and we don't know what sigma is, we have to make up for that extra uncertainty. So that's plus or minus t times the standard error. Okay, so now we have to look up what t is going to be. So let's write this down. 98 plus or minus t. Now, what is t going to be? Well, t is dependent on the sample size, right, and our confidence interval. So let's go to our t table. We'll move this out of the way, and I'll get to my t table. By the way, I think I made an extra area on Blackboard where I'm starting to accumulate tables for you to be able to use. Okay, so t-score, here's the t-score. Now, it does a little funny thing with the samples. And instead of displaying the sample size, right, you're never going to have a sample size. You're never going to have a sample size of 1 because it doesn't make any sense. It uses degrees of freedom instead, right? Degrees of freedom is the sample size minus 1. So degree of freedom 1 is really a sample size of 2. So in our case, we've got 25, which makes 24 degrees of freedom. And if you look at the top here, this is a 90% confidence interval, 95, 99. So it gives you some others as well, less frequently used confidence intervals. So 95% confidence interval, which is 2.5% in each tail. This one says right tail, but it really implies that it's both, if this is right tail, since it's symmetrical, the normal distribution, the right tail is 2.5%. The left tail is going to be 2.5% for its total area of 5%. So 95% confidence interval. We're going to go down this middle row. It's almost middle row. And go down here. It's going to be 2.064. So I'm going to go back here. What's this? Why did that open up? Okay, let's close that. Okay, so let's go back here. And 2.064. 2.064 is going to be our t value for 95% confidence interval. Now notice 1.96, 2.064. When I multiply by the same standard error, right, it's still going to be 10 over 5 because we're using 10 standard deviation to estimate sigma. It's still going to be 2, the standard error. But now our margin of error is going to change. 98 plus or minus 4.128, I think. Right, so now look at our margin of error here and look at it here. We're adding and subtracting a bigger number, so our confidence interval is going to be wider. Right, so that's going to be, and hopefully I'll get this right, 94, 93.8. I'm going to round this one, 387, comma, and on the other end, it's 90, it's 4 added to that is 102.13. Okay, I'm just rounding it off so I can get this done a little bit quicker. Okay, so that's going to make, notice how that's wider because of the t-score. Had it been a bigger sample, then that t value, if you look at the t-table, as you increase the sample size, right, as you go up the table, notice how the t-score becomes, for 95% confidence interval, becomes a smaller and smaller number. Look at 100, it's 1.98, right? It's almost the same as the z-score. And when you have the entire population, or infinity, it's 1.96. So that's why when you get a big sample, you say to yourself, gee, I'm so close, maybe I won't bother going there. Now, between me and you, when you do this for real, you want to use the t-score. You know, if you use this on to calculate a confidence interval or paper you're publishing, and it's even like a sample size of 80, you're going to want to use the t-score. You want to use the real thing, the real Megillah. Now, as it happens, in the future, you're probably going to be using SPSS to do a lot of these calculations. And SPSS has its own built-in infinite t-table. It's actually the formula to calculate t-value that has built formulas that has built into it. So it always uses, it doesn't matter if it's a sample size of 5,092, it uses the value of t, even though that might have been 1.96001, instead of using 1.96. Usually by the time it rounds up and rounds into its tables, you won't even notice the difference. But it actually does do the calculation for t every time, regardless of how big the sample size is. Okay, so that's where we stand there. So I want to just take a second here to ask you guys, how are you guys on this so far? You guys okay with this? I want to move on now to do confidence interval for proportion. Okay, good. All right, good. So let's talk about proportions now, right? Because that a lot of people find that a little bit challenging as well. The difference. Now, most of the time, almost universally, when we deal with proportions, we're going to be dealing with the z-score, because we're usually going to have a situation where the sample size is big enough that we don't have to worry about using the t-table. Okay, so this time I'm going to talk about the percentage of people, percentage of children that are lead poisoned in a certain area of the city. Let's say we're taking a grid in the city, a area where there's an older housing stock that's likely to have a lot of lead soldered pipe in it, or lead paint, and so on and so forth. We want to know what the proportion of lead poisoned children is in that neighborhood, right? So we can't go and test. We can't. They do screening, when kids enter school and stuff like that. I'm not sure what age, 3 or 5 or whatever, but they do screening, I think, of most kids these days. I'm not sure what the policy is right now, but they do screening. But let's say we're looking at 8-year-olds who probably aren't screened regularly, and we want to sample 8-year-olds to see how that population of 8-year-olds, what proportion of them are lead poisoned. Now, when we say lead poisoned, it's a continuum, right? Any level of lead in your blood is bad for kids, right? That's not good for them, right? So rather than lead, we're going to call it an action level. Which kids are above the action level, right? In which case you want to, alert the parents that maybe they should keep their eye open for lead sources in their home or something like that, right? So I'm going to say that we go and we sample, let's say 1,000 kids in this area, or maybe an entire city, right? Maybe Cleveland, or maybe New York, maybe the entire city. They're randomly selected, 8-year-old kids that are randomly selected from all over the city, right? So out of those 1,000 kids, we find that 200 of them are above the action level. Maybe that's 5 micrograms per deciliter of blood, right? So maybe 200 of them we find are above the action level. I don't want to say poison, because maybe most of them are 5 or 6. In other words, if it had been 1 microgram less, a microgram is practically nothing, right? 1 microgram less, they wouldn't have made the list, right? So maybe some of them are much higher levels. But right now, we just know We want to know what proportion are above the action level, maybe because we want to be prepared to have an idea of how many contacts we're going to have to make with the children's parents, right? That's actually might happen. Okay, so let's say what we want to find out what the real proportion is, right? So let's see. The true proportion we're going to call P. Just like mu, P is a population parameter. It's unknown, right? But we do have from our sample, we have P cap, just like we had X bar. P cap represents the sample proportion. So our sample proportion, P cap, is equal to 200 over 1,000. Over 1,000. Out of 1,000 children, 200 of them were above the action level, which is equal to 0.20. So that's our average for that sample. But we don't know we want to know what the population proportion is. So what we're going to do is we're going to calculate a 95% confidence interval for the true population proportion for P. And where we're going to calculate that is we're going to, just like with the mean, we're going to say it's equal to P cap plus or minus a value of T or Z. Well, since we're a large sample size, both of these are over 15, we're going to say Z. So for 95%, it's 1.96 times the standard error for the distribution of, if you took standard error is based on if you took repeated samples of size 1,000 from this population, what would that distribution look like? So what is that standard error? How do we calculate standard error? Well, standard error, when we're dealing with proportions, is equal to the square root of the proportion. Now, we don't know what P is, so we have to use P cap, right? So I'm just going to leave it a P, but you understand that that's really P cap, times 1 minus P over N. All of that is underneath square root sign, not just that. Okay, so what does that equal to? That's equal to 0.2 times 0.8 over 1,000. And then we take the square root of the whole thing. I'm going to get my calculator out to do this. Okay, so let's see. 0.2 times 0.8, okay, divided by 1,000 is equal to that, is equal to 0.000016. Okay, and it's a very small number because when you take square root, it becomes a bigger number, right? 0.2 times 0.2 is 0.04, right? So so when you go the opposite direction, it turns out to be a bigger number. Well, if I click on this, it'll give me the square root, and it turns out to be 0.0126, 1.264. I'm going to just call it 0.0126. Actually, for our purpose, I would suggest you keep that extra decimal place, 0.0126 at least, right? Or even if you're working with Excel or with your calculator, even store that in memory and just keep the whole thing, right? But for our purposes right now, to keep it simple, I'm going to call it 0.013. Okay, 0.013 is our standard error. 0.013. Okay, so again, I rounded. I encourage you not to round it as much as I am. You should have more time when you do your homework or on an exam. Hopefully, there won't be too many questions. So that's our standard error. So P cap, which is, let's see, what do we calculate? It's 0.2 plus or minus 1.96 times our standard error, times 0.013. Okay, so now let me calculate what my margin of error is. And I'm going to go back. And in fact, since this is here, I'm just going to multiply it by 1.96. And there's my margin of error. It's roughly 2.5%, right? 2.025, roughly. You want to know something? Since I'm here anyway, I'm going to put this into memory. That's my margin of error, and clear. Okay, so that's stored in memory right now. Okay, so actually I'm going to wind up doing this more accurately than I had even mentioned. Okay, so yeah, take advantage of your tools like using Excel and stuff like that to do this kind of stuff. So what did I say it was? I said it was 2.5%, right? So our confidence interval is 0.20 plus or minus 0.025, 2.5%. So this is my margin of error for my proportion, just like it was my margin of error when I was working with a mean. Okay, so what does this come out to? If my rounded version of this is going to be 0.175 to 17.5% to 22.5%, right? So that's my rounded version. In real life, if I had used the real numbers, let's just see what it would have looked like. Okay, it would have been 0.2 minus, I'm going to recall that, right? Pretty close, 0.175, only that last decimal place is off. Right, so my rounding didn't hurt me too much this time. And 0.2 plus my margin of error, which makes this 0.2247. Right, again, didn't hurt me too much. I wound up in the same place. Won't always happen. Don't do as I do as I say. Right. So anyway, so that's our confidence interval. So what does that tell us? That means that we're between that we're we're 95% sure that the true population proportion is between 17.5% and 22.5%. So what does that mean first? That means if we have a population in our city of 10,000 or 20,000 children in the age range that we're interested in, that we have to be prepared to deal with the number of calls and follow-ups that we have to make of 17.5% to 22.5% of these children. I have an idea now, a better idea now, of how much I need to budget and how many people I need to employ to make sure that I can reach all of these. If I'll go for the upper end, I'm saying to myself, I'm 95% sure that I won't miss any kids if I budget enough to do 22.5% of these 20,000 children, whatever that is. That's going to be 4,500 children or something like that out of 20,000, right? So that's one of the ways you might use this. Now, while I'm bringing this up, I just wanted to bring up that somebody had mentioned to me, they saw these other formulas, like the mean proportion is equal to n times p, and the standard error is equal to the square root of n times p times 1 minus p, and so on. It doesn't really jive with what we're doing here. Well, this is how you would work with a proportion when you actually are looking at the probability of, if you took a sample of size 1,000, what's the probability of getting a certain number of people out of that 1,000? I'm going to take this example I have here. Let's say that n is equal to 1,000, and you know that the population proportion is equal to, true population is equal to 20%. Well, n times p, 20% of 2,000, the mean number of people you would expect every time you took a sample of 1,000 is 20% of 2,000 is 200. That's the mean number of people that you would expect. Now, if you took another sample of 1,000, you might get 188, or another one you might get 192, or another one you might get 212. So this is looking at the distribution of, if you took repeated samples of size 1,000, the distribution of the results of those, how many people, not what proportion of, but how many people you would get on either side of this 20%, and what that spread is. And this gives you the standard deviation. We call it standard error because we're dealing with repeated samples. The standard deviation for the spread that you would expect for around 200, it's really 200. And whether or not that, the range of 95% of those would be 170 to 230 or something like that, right? Same idea as this, but you're dealing with the actual numbers of peoples, not the proportion that you would get from each sample. So if you see that come up, I'm not sure that was broached much in lecture, but if it does come up on a problem or in the lecture in the future, let me know in the discussion boards on, where I put the online questions and stuff, the review questions. Let me know that it came up somewhere, or if it confused you, and I'll go over it again in the future. Okay, so that's how we would deal with these kinds of problems, okay, for proportions and means. Well, now we went and complicated this whole thing with this thing called a t-test. Okay, so I'm going to say don't save. Okay, and I'm going to close this. Okay, so let me get a fresh piece of paper here. Okay, so let's talk about the t-test. Well, in this case, what we're doing, whoops. Okay, how do I make this go away? Okay, good, nice click, it went away. Okay, so when we're dealing with the t-test now, what we're doing is we're using a tool where we're comparing two means. Okay, we want to compare, we spoke just briefly now about the mean blood pressure. Whoops. Mean blood pressure. And I think I mentioned that we might have two populations we might want to compare. We might want to compare people who are vegans versus people who eat meat for their blood pressure. Right? Now, of course, you want to control for all the other compounding variables. Are they smokers? We want to make sure that our population is defined. The two populations are defined. Non-smokers between the age of 40 and 60, and all male, let's say all female, right? And let's see, what other factors there might be. Maybe I want to control for BMI, normal BMI between 20 and 30, so within that range. And we randomly select people from these two populations that meet these criteria, right? So I randomly select vegans, and I want to compare them to people that eat meat. Okay, so let's say that the populations of vegans in this group is pretty small. Let's say we only have in this population, maybe we're looking at a nursing homes or something like that. Let's say that this population is relatively small, so there's few enough of them that I could sample every one of them. So I know the mean for vegans is equal to, mean blood pressure for vegans is equal to 90, right? Maybe a diastolic, maybe I'll call it 80, right? In that age range, versus people that eat meat within this group, right? Well, there's some, like vegans, I was able to sample every one of them because there probably aren't quite as many of them, especially real vegans that don't eat like cheese and stuff like that or eggs, right? Then I don't know, vegans eat eggs? I don't think so, right? So no animal products at all. So that they're rare as hen's teeth, let's say, right? Not to bring up a meat analogy. So at any rate, so not many vegans. I got a shot. Maybe I could sample every one of them. Really know what the mean is for vegans. But meat eaters in this population, that could be 10,000 of them or something like that. That basically it's everybody else, pretty much, right? So, or maybe I'll call that non-vegan. So we even include vegetarians, right? So it's impractical for me to sample everybody. So I'm going to take a sample size equal to, let's say, I think a sample size of 100. Okay, so I take a sample size of 100. I calculate the mean for those non-vegans, and the mean X bar comes out to be 90. Okay, okay. So now I have a little bit of a problem at this stage, right? One is that, okay, means 90. It's different than vegans, right? But is that difference just due to chance because of this people I happen to sample, or is that difference so great that I can rely on it to be statistically significant? In other words, have a small chance that I would get that different a result from 80 to 90 had there been no difference between vegans and non-vegans. I'm actually going to call. I'm going to make it a little bit closer. Call it 85. Right? Is that big difference big enough for me to make a difference? For me to imply a difference? Well, I can look at this two ways. Since I know the mean for all vegans, there's a shot that I also know the standard deviations for vegans, right? Let's say that's equal to, the standard deviation is equal to 10. Well, for the moment, I'm going to assume that the standard deviation for vegans is equal to the standard deviation for our population, for our non-vegans, right? So if I do that, well, gee, I know the standard deviation then. I calculate X bar, so I should be able to calculate a confidence interval for non-vegans and see if that confidence interval includes 80. And if it doesn't, I'm 95% sure that my true mean blood pressure for meat eaters, non-vegans, excludes that 80. Well, that means I'm 95% sure that the mean for non-meat eaters is different than 80. Even if it's 81, even if it's 81 to 89, right? I'm 95% sure it's between these two numbers. That means I'm 95% sure it's not 80 because 80 is outside of that range. We got another way of doing that. Another way of doing it is to calculate how many standard deviations apart that X bar, the mean for our estimate of the mean for non-vegans, is from the known mean for vegans. And we're going to call that Z, right? That's a number of standard deviations apart. How far apart are they? Well, the distance apart that they are is equal to X bar minus mu, our known mean, over the standard over the standard error, right? So, and we have a sample size of 100 there, right? So over the standard error. So we want to know how many standard deviations apart there are. Well, we know it with the z-score. If the z-score is 1.96 or bigger, we know that there's less than 5% chance that we would have that big a difference and have them come from the same population. So we're going to use the 1.96 as our critical value to decide whether or not we're going to say that they're different. That's the same thing as saying that we're going to accept that we can have up to 5% chance of being wrong. Alpha error is equal to 5%. So let me calculate that and see what it comes out to. So X bar is 85 minus 80 over the standard error. Now, the standard error is going to be equal to our presumed sigma. It's going to be 10 over the square root of the sample size, which is 100, which is 10. So our standard error is equal to 1. So now, I'm going to make this 83. Notice how, you've noticed that I do this occasionally with the examples that I use in class that are on the example sheet, that you'll notice that when you go to the answer sheet, I've changed the numbers a little bit to make it a little bit more interesting. The reason why I did that is it's going to come out to be 5 over 1. That's 5 standard deviations. We can't even look that up on a table, right? The probabilities are so small. So I'm going to make that 83, right? 83 minus 80. So I'm going to put that over 1, the standard error. So this is equal to a standard error of 3. Okay, Z is equal to 3. Now, how likely is it for these two means to be that far apart? If I go to the Z table, right, I can find where minus 3 and plus 3 standard deviations are, right? And the area of these two represents how often we would get that big a difference if they were from the same population. So I could look up 3 or negative 3 because the areas are the same at the top and the bottom. I'm going to go to the Z table to look that up. I'm going to take a break and take a look at the, I'm going to ask you on the chat in a second, like how you feel about this so far. Okay, to make sure we're all keeping up. I'm going to go to Z table, and I'm going to look up what's the area to the left of a Z-score of 3. Okay, so 3.00, that's 1/10 of 1%, 0.0013 is that area. Okay, so I'm going to go back here, and you'll notice that if I go to plus 3, well, plus 3 is 99.87. We'll notice that 0.0013 is really just 1, subtracting this from 1. So like in other words, this area to the left of plus 3 is 99.87. So that leaves 0.0013 in the right tail. So we got 0.0013 in the left tail, 0.0013 in the right tail. Right. So those two extremes are the probability of being wrong. In this case, probability if we say that the two means are different, what the likelihood is that we're wrong is equal to 0.0013 on this end and 0.0013 on this end, right? So you'll notice that when we calculate P, the probability of being wrong, in this case, if we say that these two means are different, is 2 times 0.0013. We call that a two-tailed test when we include the probability of guessing high and guessing low. The reason why we do that is because it's more conservative to do this test, and also because very frequently we don't know going in whether we don't have a good reason to believe for sure that we know whether meat eaters have a higher or lower blood pressure than vegans. Could be vegans eat a lot of fats from fatty oils and stuff like that, or have some other reasons why, or maybe they're vegans because they have other health issues and so on and so forth. So we don't know going in if it's going to be higher or lower. So we include both possibilities, +3 and -3. So we double that. So the probability that we would get this extreme a difference between these two means or bigger is going to be 0.0026, about almost 0.3%, right? So we're willing to tolerate the probability of being wrong of up to 5% in most studies, right? Where otherwise, you would never know for sure. So in a lot of studies, we're willing to accept 5% chance of being wrong. So since our probability of being wrong, if we say that they're different, is less than 5%, I'm going to say, I'm going to say that I can say with statistical certainty, not real certainty, right? I can say it's statistically certain that the difference between these two groups is statistically significant, right? There's less than 5% chance of my being wrong if I say that. Okay, now, in reality, we rephrase this. We start this by saying, let's start not with this calculation, let's start with a hypothesis. And in this case, our hypothesis, H null, right? Our null hypothesis. Null means there's no difference, right? Null, none, right? Is mu for vegans, the mean blood pressure for vegans is equal to the mean blood pressure for non-vegans. Okay, and our alternative hypothesis is that the mean for vegans does not equal the mean for non-vegans. So notice I use mean, not mu, not X bar here, right? Because we're talking about the means for two populations that we're really concerned with. So in this case, because my probability of being wrong, if I say they're different, in other words, reject the null hypothesis, if my probability of being wrong is less than 5%, which it is, I can reject the null hypothesis and accept the alternative hypothesis. Now, had I said instead 81 instead of 83, then the z-score would have been equal to 1. And if I went to my z-table, you would have found that for a z-score of 1, each tail is 4.13, each tail for a z-score of 1, where is it? There it is about 16%. I'm going to call it 16% for our purposes. Is about 16%, right? So 2 times 16% would have been 32%. So our p-value would have been 32%, which is way bigger than 5%. So there's a really good chance that we would get an outcome, even if these two populations were not different, that we would get that big a difference, because there's not enough difference given the spread for us to know that that's really true. Okay, so that's how we would do a t-test in this particular case, where we knew the standard deviation, or we assumed that we knew the standard deviation. But you know something? We got another problem here. Most of the time, we really don't know the standard deviation of the population that we're drawing our sample from. So you see where this is going next. We're going to have to use t instead of z, right? So again, in this case, 0.32, we fail to reject the null hypothesis. We don't accept the null hypothesis. We just say we fail to reject it because we haven't proven that this is true. We've only comes short of being able to reject it, right? So the two terms you might use here is reject the null hypothesis and accept the alternative, the first case where the probability of being wrong is very low, or fail to reject the null hypothesis where the probability of being wrong is relatively high. So I want to do another example here, okay, and then I'll go through a couple of questions. And okay, don't save. Let me try this. I'm going to do the same thing, except this time I don't know what the population standard deviation is. Okay, again, I'll reiterate what we have here. Okay, this time I'm going to start. H null, mu for vegans equals mu for non-vegans. And our alternative hypothesis is mu for vegans does not equal mu for non-vegans. Okay, so this time, let's see. Again, I'm going to say 80. Okay, mu for the vegans means known. It's 80. Okay, but all we know for the non-vegans is x bar. That turns out to be equal to 83. I'll use the same numbers before. Okay, and this time my sample size is equal to 25. Okay, and gee, what am I going to do for standard deviation? Nobody only told me what the mean was for the population of vegans. Nobody told me, and maybe I do know it. Maybe I know what sigma is for vegans, but I don't want, I have no evidence to say that it's the same for non-vegans. Maybe it's a bigger spread for non-vegans. Maybe it's narrower. Maybe I decide I can't rely on that. So what am I going to use for standard deviation? Well, the only thing I have is the same way I found the mean is the 25 people that I sampled at random that were meat eaters in this population. Turns out that is, I think I called it 10 before. I'm going to use 10 again. Okay, so standard deviation is equal to 10, except this time we're guessing. We're using this as an estimate of sigma. We don't know what sigma is. What does that mean? Small sample size. We don't know sigma. We have to use the t distribution. Okay, well, when we use the z distribution, and we were willing to have up to 5% chance of being wrong, up to 5% chance of being wrong, when we use z, right, we said to ourselves, since we know sigma, we can use z, and we know that the value that we're going to use for the left and right was equal to 1.9 standard deviations. We wanted these two values to be at least 1.96 standard deviations, because if they are, we know that the tails on either end are lower than 2.5%, and when you add them together, they're less than 5%, right? So we use z is equal to 1.96. Well, now I can't do that. Now, in order to keep my alpha is equal to 0.05, have less than 5% chance of being wrong, I have to use the t value, which is a bigger number this time, right? And the t value is going to be dependent on the degrees of freedom. So we're going to have to look that up from a table. And in fact, we could go to the table right now. We could see that for 24 degrees of freedom, I think I ducked it down here. Whoops. There it is. For 24 degrees of freedom, t is equal to 2.064. So we have to be further apart. On those two means have to be more than 2.064 standard deviations apart for me to have a p-value that's less than 0.05. Now, using this table, unlike the z table, I'm not going to know for sure what the p-value is. I'm only going to know if it's bigger, the t-value is bigger than that number, then my probability of being wrong is less than 5%, right? Z-value is nice because it gave me a nice clean p-value I can compare to 0.05. And in fact, SPSS, because it has tables for all the t-values and all the percentages for every t-value, t-table that you could have based on, regardless of the sample size, it'll actually give you a p-value, a probability of being wrong. But for us, we're just satisfied knowing that if we are at least this far apart in the two means, unlike 1.96, which was what we would say is good enough if we had if we were using a z-score, this has to be 2.064. We call that our critical value of t. If we had a sample size of 16, our critical value would be even bigger because we've got to be further apart to have that level of certainty that that there's less than 5% chance of being wrong. So now, because it's a smaller sample, they have to be further apart for us to be have that level of certainty. Okay, so let me do this. So 2.064 is what our critical value 2.064. That's going to be called T critical. I need to get a T value that's bigger than that to be sure that my P value is less than 0.05, less than my tolerable error. Okay, so let's calculate what our T value. T is equal to, not surprisingly, X bar minus mu, the known mu, over our standard error. Okay, so X bar, minus mu, X bar was 83, minus 80 over our standard error, which was turned out to be 10 over, oh, hang on a second, sample size is only 25. So our standard error is equal to 10 divided by the square root of 25 is equal to 5 is equal to 2, right? So a standard error is equal to 2. So let's see what our t-score is. Our t-score is equal to 3 over 2 is equal to 1.5. Well, gee, look at this. We have to have a t-score bigger than 1.5 to reject our null hypothesis. So in this case, because we have a small sample size, most of these numbers are the same as before, right? We knew what sigma is, so we could work with the z-score and so on. But now we have a sample size which increases our standard error, and we also have the extra uncertainty of the t-score. So since my t-score, in other words, these two values, 83 and 80, are not enough standard deviations apart based on my t-values, they're not enough t-scores apart, then what happens here? This time I fail to reject the null hypothesis. Okay, had we been working with 85, if this had been 85, then this would have been 5 over 2, which would have been 2.5. Well, now my t-score, these are far enough apart, they're 2.5 standard deviations apart, 2.5 t-scores apart, and all I needed for this sample size was 2.04, so I can reject my null hypothesis and accept my alternative hypothesis. Okay, good. So now, the proof of the pudding now is I'm going to ask you how you feel about this. Are you guys reasonably comfortable with that? Anybody still awake out there? Have I put everybody to sleep? Okay, good. So that's really the basics of all this. Now, I just want to point out, I want to show you, I want to answer a couple of questions here that came up. And, you know, I'm going to have to post I'm not going to have time to go over the exercise 2, which I was hoping to do today, but I will post the solutions up to it between today and tomorrow. Right, you already have solutions to exercise 1, which is examples like this. Okay, but I do want to approach a couple of questions, and that is, let's see. Okay, this one came up. Let's see if we can make that bigger. I can read it. I can't. I know that we use Z for large sample and T for small sample. What am I think I answered that question, right? We discussed really relative. What's a large sample? What's a small sample? Okay. Can we address here we go. Okay, you can address the null value in the formula. Z is equal to X bar minus null value over the standard error. Null value represents the known mean. In other words, it would be X bar, which is our sample mean, minus by null value what the known mean is that you're comparing it to. Okay, that's for a single sample t-test, right? So you could just say that's mu, the known mean, right? That might be from the book or something like that. Maybe they use that expression instead of just putting in mu or something like that for a single sample t-test. The other thing came up is one of the an assignment. This is for you guys that are in the brick and mortar course. This was an assignment in the online class. Let me open that up and I'll go over that. You guys will benefit from it anyway. Yeah, just if you notice that they misspelled my name when they created my login. So rather than chance having them change it and destroying everything I have on Blackboard. I'm living with typing in my name spelled incorrectly. Okay, let's see. I think it was assignment 6, problem 7 that came up. Okay, assignment 6. Single sample hypothesis test. Okay, let's see what we have here. So, problem 7. Oh, okay, so it's part of this other problem here. It continues from 5. Using the data above. Okay, let's keep going back. How far back do I have to go here? Continuing the problem above. You wish to test whether the number of fouls in regular season games is different than during the NCAA tournament. Basketball we're talking about here. The mean number of fouls called during all regular season games, mu is equal to 40.1. They kept track of it, so they know exactly what it is. During 16 randomly selected playoff games, the mean number of fouls, this is a sample now based on 16 games, mean number of fouls, the sample size is 16. The mean number of fouls in those 16 games is 38.1, and the standard deviation of the sample is 5.8. So we know we don't know mu, so we know we're dealing with a t-value here. It's a small sample, 16. So the mean x bar is 38.1. We're going to wind up comparing it to mu for the regular season, which is known, which is 40.1. You calculate 95% confidence interval for the mean number of fouls called during the playoff games. The lower value of the confidence interval is okay. So how would we calculate that? Well, first of all, since we don't know sigma, it's going to be t. We're going to use x bar, right, for the we're going to calculate confidence interval first for 38.1 before we do a t-test. It's going to be 38 plus or minus the t-score that we need for 15 degrees of freedom times the standard error. And the standard error is going to be 5.8 divided by 4, the square root of the sample size. Right? So we would calculate the margin of error and add and subtract it to 38.1. You should get the right answer for the upper and lower values. That's not where the question was on number 7, but I want to go through these a little bit anyway. Okay, so from that point, using the data above, you perform a hypothesis test comparing the mean number of fouls during the regular season game and during playoff games. Your null hypothesis is mu regular seasons is greater than that. Mu regular seasons is greater, less than equal to. Mu regular season is not equal to. Well, since we didn't know ahead of time whether our sample is going to be higher or lower, it's going to be mu regular season is equal to mu playoffs. Typically, for a two-sided hypothesis, there's just an equal sign. Some of these may be applicable to something called a one-sided hypothesis. We'll talk about that in the week or two coming up. Okay, so this would be typically what we would use as our null hypothesis. And what would be our alternative hypothesis? Well, as we discussed before, our alternative hypothesis is that they're not equal to one another. Again, this is a two-sided null hypothesis and two-sided alternative hypothesis, because we just said they're the same, but they're different because we didn't know ahead of time, as we often don't, whether one is going to be greater than the other, which one's going to be greater than the other. What is the critical value of t that you would need to exceed to reject the null hypothesis with alpha errors equal to 0.05? Well, since this is a t-test and the sample size is 16, we'd have to go to our t-table. If I can find it now, let's see. There it is. There's our t-table. Nope, I got the wrong one, I think. There it is. Go to our t-table. Whoops, that's our z-table. Let me try that again. Okay, why didn't it come up front? Oh, there it is. Okay. So we go to our t-table. For sample size is 16, 15 degrees of freedom. Our t-value have to be exceeded is 2.131. Okay, so the two means, the 38.1 and the 40.1 or something like that, they'd have to be at least 2.131 standard deviations apart. That would be our critical value of t. Given the data above, what is the value of t that is associated with the difference between the regular season mean and your sample mean? Well, t is going to be equal to x bar, 38.1, minus mu, which was 40.1, right, over the standard error, which is 5.8 divided by 4, which is, I don't know, roughly 4.2 or something like that, 1.2 or something like that, right? So we'd come up with what the t-score is in that case. You know, I'm going to use this as an excuse to take the table that I made up for you guys. Let me find it. Okay. It's here, I know it. Oh, here it is. Okay, good. I made up a spreadsheet for you guys, kind of help you out. Really, my intention is for you guys to use this to check your work, not to cheat and use it to do the calculation. But I'm going to use it right now to do this calculation. Okay, so the way that this works is you have two pages here. You got confidence interval for means, and you got confidence intervals for proportions. So I'm going to go for confidence intervals for means. It also will give you information on the t-values and t-tests and so on and so forth. Okay, so, actually, I didn't do t-tests. I did confidence intervals. So let's calculate confidence interval. So in this case, it's for a mean, not a proportion. For proportions, we would fill in the number of people, like on our example before. Well, we had 200 people out of 1,000 people, right? And we calculate our, out of 1,000 people. It didn't work. We knew it didn't work. Out of 1,000 people, and there it gives you our confidence interval for 95%. It gives you the z-value that's used in the margin of error, and so on and so forth. Notice I only calculated z-values and confidence intervals for proportion. Now, if I go to confidence intervals for means, if I go up here, mu was equal to 38.1, right? And standard deviation was equal to, you don't calculate confidence interval for known means, right? I really should just put X bar here, right? Because you don't really calculate confidence interval for a mean. You know what the mean is. You don't need a confidence interval. That's what I think. Standard deviation was 5.8 of the sample, and the sample size was 16. Coincidentally, happens to be right. And this will calculate for us, as I described the sample before. This will calculate for us. Well, the z-value that we're using, well, look, I can't use the z-value here, can I? Because it's a small sample size, and I don't know sigma. Right, this one should just, I have to change that. I have to unlock it and change that, because the only thing you can change in here is those numbers. I got to go down to the bottom part where population sigma is not known. It's a small sample size. Well, the t-value is 2.13 for that sample size. The margin, is that right? Let me check that right now. For 15, 2.13, sure enough. I might have underneath here, it might actually be a bigger number. Yeah, it actually is the real number. I just took that whole column and rounded it to 2 decimal places. But it really uses 2.131, so on and so forth. Okay, so in this case, the confidence interval, the margin of error based on that being t, and the standard error that it calculated based on this number, which is 1.45, 5.8 over 4. Okay, the margin of error is 3.09, and the lower confidence interval for 95% is 35.01. The upper is 41.19. So you could do this manually, and then go back, do the calculation yourself, and then go back and you can use this to check your work as well. Okay, so you might want to give that a try. Okay, let me know if you have. I'm gonna be putting that. There's a. I kind of deleted this because I wanted to wait until I got a chance to go over it with you. But just like there was exercise 1 that I gave you the answers to that are up there now, I also have some more examples. An lab exercise set 2. Which has a lot of these kinds of examples. Like, for instance, mean number of close friends at 5.7, standard deviation 1.3, fixed number of close friends, significantly different mean of population. You give it the mean of population, but small sample size, and so on and so forth. And they ask you to null alternative hypothesis, calculate, decide whether to use the T or Z, and then give you conclusions. I'll post this with answers later on so that you get a chance to get some more examples as well. Okay, so also, by the way, the book has a lot of examples along with the answers at the back of the book. Pretty sure your version of the online text has the answers just as mine does. Okay, so we've been doing this for a while. We're doing an hour and a quarter now. So I hope that helps. I think that should give you kind of an idea, an outline for when you read the problem. I know in computers they use the expression parse, right? So, like in other words, if you read a computer instruction, you can parse it into part. You parse it means like you can kind of break it up. Well, this is the part that describes the object you're working with, and this is the part that describes this property about it, and this part that tells you what you're going to do with it, and so on and so forth. Also, with grammar, right? You parse sentences in grammar. This is a noun. This is an object. This is a verb. When you look at these problems, a big part of the problem is parsing it, figuring out from all of the. We like to dress these up with a lot of camouflage, right? So we describe these rather than just a problem. A mean X bar, so to give you numbers, we give you situations. This is a population, so this is their age range, so on and so forth. A lot of stuff that's not relevant really to the calculation, but if you read the problem carefully, you can see what you need, the information you need, which is the mean for single sample t-test. Well, since it's a single sample, I'm going to be comparing it to a known mean. What is the known mean? What's mu? What's X bar? What's the sample mean? What am I going to use for standard deviation so I can calculate standard error? What's my sample size? Do I know sigma for standard or do I know standard deviation? So that means I got to choose which to use, Z or T, and so on and so forth. So you got to kind of parse these things a little bit to break them down into the elements that you need to solve the problem. Sometimes that can be the most challenging part of this thing. So I hope these examples that we just went through kind of give you a insight into how to approach these problems. Okay, and I agree, you need more problems. I'll get you more examples. Okay, so have a good rest of the weekend. I'm sorry to say spring break is over.